functions. A composed function is a function made up of one plugged inside of another. Okay, so examples would be the square root of tangent. Okay, tangent is plugged inside of the square root. It's composed inside of the square root. Or another example might be e to the 0.5x. The linear function 0.5x is plugged inside of e to the, whatever. I mean, the basic form is e to something, and you've plugged in 0.5x instead of just plain x. Some other examples that, this one comes up a lot, so that's why I was kind of mentioning that. Or you might have a polynomial plugged inside of a higher power. And so if I were you, I would leave it in this composed form rather than having to, work that out and multiply the whole thing out 4 times. That would create a big mess, okay? So these are examples of composed functions, and that's when the chain rule comes into play. So the derivative of a composed function involves the derivative of the outside function, okay? So you figure out who's the outside, and you figure out what its derivative is, and you leave its input as it is, okay? So if you were figuring the derivative of the square root, tangent's going to stay plugged in the derivative of the square root. Don't change the input. So if you figure out the derivative, we could actually do this one, okay? There's nothing stopping us from doing this one. We know enough stuff at this point. What does the power rule tell us to do if we're taking a derivative?
4.
You're going to multiply 4, and what will be the new power? 3. I leave the input as it is, okay? I'm not done with this problem yet, okay? I haven't finished my rules, so I'll hold off a minute. Once you find the derivative of the outside, and you make sure you've left its input as it is, then you multiply by the derivative of the inside function. If you work on word problems where you can tell the units of the inside and the outside, why we do this ends up making sense. So again, we're short on time tonight, so I'm not going to start to drag one out, but trust me, on a group quiz or on a homework assignment or somewhere, we'll work through one. But for example, if you know that your car gets so many miles per gallon, and you know that you're driving at a certain speed, if you think about how you cancel those units to figure out how many gallons of gas you need to go a certain trip, you'll see that you're multiplying the units like this. Okay, you're multiplying the units of the rate of change of miles per gallon with the speed that you're going. And it works out nicely. That's a very good example of seeing this. So to finish this problem, what am I going to multiply by? 2x, okay, why 2x? Power rule. So I multiply by the old power, and then I subtract 1, but what's 2 minus 1?
1.
Okay, on Tuesday, so it's just 1. So then on Tuesday we talked about x. What was x's derivative?
1.
It's just the constant 1. Okay, and we looked at it a couple different ways. We thought about it in terms of the slope. The slope of this is 1. And then tonight we talked about constants. What are the derivatives of constants?
0.
0. Okay, so I could clean this up a little bit more if I wanted to. I could rewrite that as 8x plus 4. I would probably then just leave it like this. I wouldn't bother trying to cube that out. It would end up being messier than necessary. Okay, so that's the chain rule. it down over here. Okay, so the derivative, it involves the derivative of the outside function times the derivative of the inside function, but don't mess with the input of the outside function. Leave it as it is. Okay, so we did chain rule, and we did quotient rule. And I have derivatives of sums and differences, but I kind of just, it's what you think it should be. The derivative, here's a sum, okay? I have a sum here. Its derivative involves finding the derivative of the terms, and you add them together, okay? That's all that means. Okay, so we've talked about that. All right, so we have the trig functions, and then the log functions, and then we have a to the x. And then we will have our completed list. Can I erase this so people kind of right? Okay, so tangent we mentioned is sine over cosine. So if I take it in its quotient form, then the derivative would involve the denominator times the derivative of the numerator, sine's derivative is cosine, minus the numerator times the derivative of the denominator, cosine's derivative is minus 1 times sine, all over the denominator squared. Cleaning that up, I get cosine squared plus, because these two negatives, subtracting a negative will make an addition. And hey, that's the most famous trig identity. Cosine squared plus sine squared equals 1. Alright, and this is more commonly written in the solutions manuals or whatever, it's secant squared. So tangent's derivative is the function secant being squared. Okay, so tangent, f of x equals tangent, then its derivative is secant squared. Cotangent works out basically the same way. Cotangent is cosine in the numerator, sine in the denominator. If you work it out like we just did, then you end up with negative cosecant squared. Okay, but you would do the proof the same, very similar to what we just did. It's just cosine's the numerator and sine's the denominator, and you end up with negative cosecant squared when you clean it up. For secant, we're going to remember that secant is the reciprocal of cosine. That's its definition. And so I either could do quotient rule or I could do chain rule. I think because I just did quotient rule, I'll do chain rule. So secant, you can think of it as 1 divided by cosine and do quotient rule, or you could think of it as cosine to the minus 1 power and do chain rule. So if I do chain rule and I look at it from this point of view, my outside function is minus 1. So I'm going to multiply by minus 1, and I'm going to subtract 1 from the power, and if I subtract 1, I'll get negative 2. And then notice I left cosine inside that negative 2 power. I don't mess with the input. I leave the input alone. But then the chain rule says multiply by the derivative of the inside function. So what is cosine's derivative?
Negative sign.
Negative sign. So then this negative and that negative cancel out, and I get cosine to the minus 2 power times sine. And again, there's technically nothing wrong with that version. It's just if you look in the the list of derivative rules, it's not going to be left like that. Instead, they do this little trick where they rewrite that negative power down in the denominator. And they recognize that, hey, I could then write that as the product of those two fractions. And the fraction on the left is equivalent to what function? Tangent. And the fraction on the right is secant. Okay, so tangent times secant is the derivative of secant. Okay, cosecant has similar proof, but we're working with sine instead of cosine, so I could do basically the same little trick over there. And if I do so, I will end up with minus cotangent times cosecant. Okay, so again, it's probably a good little activity for you to try to do a similar proof like we did with secant for cosecant and work it out and see that you get minus cotangent times cosecant. Alright, so we still need to talk about a to the x and ln of x and log base b. We'll leave those for Tuesday. Okay, because I'm going to take the last little bit of time to make sure people are okay on their homework assignment.